Hi, everybody. One of the goals of derivative analysis is to find and identify extrema on functions. And there's three acceptable ways to do that. And so in this video today, I'd like to show you how we can justify extrema on functions using three different tests. And we've already talked about them: the candidates test, the first derivative test, and the second derivative test. So what I'd like to do is review the three tests in this video and then end by showing you one example of each test so you can sort of see them in action. And it's important to remember that extrema on functions will only occur at critical points and endpoints, but the presence of a critical point or at an endpoint doesn't guarantee the existence of any type of extreme value. There's a little bit more detective work to do. So to begin, here are the three tests, and kind of in summary, I thought I would show you how they work with a single function, and that single function is listed right here in yellow. F of x equals negative x minus e to the power of 1 minus x. And number one says that this function is going to be closed off on the interval from 0 to 3. Well, that closed interval is going to signify that I'm going to probably want to use the candidates test to explore what happens at f of 0 and f of 3, and then also search for any critical points in between 0 and 3. So when in doubt, we're going to take a derivative and set it equal to 0 so that I can find critical points. And I did that here with f prime of x. I set that equal to 0 and found one critical point, x equals 1. So in my candidates test table, I have the endpoints of 0 and 3. I'm going to also add that critical point of 1. And at that point, I'm just going to look at the function values of all three, f of 0, f of 1, and f of 3. And then I'll sort of do an analysis by comparing the values of all those outputs, and I'll just draw the conclusions necessary. And I did that here in the table, and it appears that my function f has an absolute maximum value of -2, and that occurs at the point x equals 1. So the first derivative test, that's the next method of finding extrema, that's where we're going to create a sign chart. So I found the critical point already of 1 in the previous part. As I build a sign chart, an f prime sign chart, I'm going to look at the intervals from 0 to 1, and then again from 1 to 3. And I'm only interested in the sign, positive versus negative, of the derivative. So I'm going to pick a test point on the interval from 0 to 1. How about 1/2? Plug in 1/2 and generate your function value for the derivative value. And I really just care about what the sign is. In this case, it's going to be overall positive. From 1 to 3, I'll pick a test number of 2, plug that in, and the derivative ends up being negative. So I have a positive derivative at the beginning. I hit the critical point where f prime is equal to 0, and then the derivative is negative. So what does that mean for the behavior on f? Well, that means regular f is increasing, and then it's decreasing. So conclusion, f has a local maximum at x equals 1 because f prime changes from positive to negative. That would be how we would use the first derivative test to verify the fact that I have a maximum at x equals 1. So far, both the candidates test and the first derivative test are basically working together in harmony. What about that last one here, the second derivative test? That is just a matter of looking for the second derivative and analyzing concavity. So here's the conclusion of the second derivative test. And then I have my derivative, f prime, as -1 plus e to the 1 minus x. That's from back in part A. Let's find the second derivative of that. F double prime is -e to the power of 1 minus x. Now I know the critical point is x equals 1. We already found that earlier. So the second derivative test says evaluate the second derivative at the critical point you find, or critical points, if there's more than one. Here I just found the 1. So what is f double prime of 1? Again, I don't really care what the value is. I just care about the sign. Well, f double prime of 1 ends up being -1, which is less than 0. And if I have a negative second derivative, then the function is concave down. And any kind of extrema on a concave down function has to be a maximum. So those are the three methods to find extrema. And I kind of like how from that one function, we can see how each method, each test, verifies the exact same conclusion that I have a local maximum on this function at the critical point of x equals 1. Now, let's actually do a couple more examples to close out this video. So here's a new function, and I'll work it out with you. You feel free to pause the video and try it on your own if you wish. Number 2 on this activity says to find, well, for all of these, it says to find the extreme values and where they occur, and then to state which method you use. Well, I have here x to the power of 2/3 as my function, and the interval is closed from -2 to 3. I'm going to probably use the candidates test here because of the closed interval fact. So let's find the derivative. 2/3 x to the power of -1/3. Now, where does that equal 0? Well, it's really never going to equal 0 because I'm dealing with an exponential function. So does that mean that there's no critical point? Not exactly. Because, remember, critical points also occur when the derivative doesn't exist. And f prime of x will not exist when x equals 0 because you can't take 0 and raise it to the power of a negative exponent. All right, there's my critical point. I'll put CP for critical point. In my candidates test chart, let's fill in the endpoints. Endpoints are -2 and +3. I found one critical point where the derivative does not exist. That'll be a 0. And now I'm just interested in comparing all three of those values and drawing my conclusion. So f of -2, you can confirm this, but I found that to be 1.587. Check that on your calculator, see if you agree. F of 0 will be 0. And then f of 3, on my calculator, I got a value of 2.08. So we're looking for the extreme values and where they occur. So I would conclude by saying that f has an absolute maximum of, looks like 2.080, and then f has an absolute minimum of 0 on that closed interval. All right, so let's move ahead. Another example, number 3. New function, another closed interval. So I've got to keep that candidates test sort of in the back of my mind because I have endpoints that I have to check. But what I'd like to do with this one is actually do the second derivative test and just show you how that might work on a different function. So let's find f prime. F prime will be, that's really x to the -1st, by the way, plus ln of x. So power rule, -1x to the power of -2 plus 1 over x. And let's see, where is that going to be equal to 0? I'm searching for critical points. So that is essentially going to happen. I can add this over here and make that x to the -2nd equals x to the -1st. So it looks like my solutions here will be x equals 1. Now, x equals 0 would also be a critical point because that would be where the derivative doesn't exist. However, look at the interval. The interval is only valid from 0.5 to 4. So I don't really need to worry about 0 for this case. My only critical point is that x equals 1. Now let's move ahead to the second derivative. Well, the second derivative, another power rule here. So that would become +2 x to the -3rd, and then minus x to the -2nd. Now, the second derivative test just says take any critical points that you found and plug them in to the second derivative. So in this case, I'm going to take my f double prime. I'm going to plug in that value of 1. I really don't care what the number is. I just care about the sign of f double prime here. So 2 minus 1 looks like I'll have a value of 1. F double prime of 1 is 1, which is positive. So I'm dealing with a concave up portion or function at x equals 1, and if x equals 1 is a critical point, it looks like looks like I'll have a minimum right there. So I would say because f double prime of 1 is positive, f has a relative minimum at x equals 1. So there we have it, a little conclusion off the second derivative test. Now, what about the maximum though? For that, the only other places they could occur would be at those two endpoints. So if I take the endpoints of 0.5 and 4 and analyze those in a little candidates test off to the side here, I found this on my calculator to be 1.307 and 1.636. So I would say that x equals 4 is the absolute maximum of f having a value of 1.636. Make sure that you don't confuse the value of an extrema, the value of a maximum or a minimum versus where it occurs. So here my absolute maximum is 1.636, but it occurs at the location x equals 4. All right, and then finally, one last example to end the video with here. So I have f equals 1 over x squared minus 1, a little rational function. I'm going to write it, by the way, as x squared minus 1 to the power of negative 1, just to make my derivative process a little bit easier here. And I haven't yet used the first derivative test, so let's do that here right now. F prime, negative 1 times x squared minus 1 to the negative second, don't forget power rule, times the derivative of the inside, which is 2x. And if I write that a little bit differently, maybe negative 2x over x squared minus 1 to the power of 2. So there's f prime, and I'm searching for critical points. Where does this equal 0? Well, the whole thing is going to be 0 whenever the numerator is equal to 0. So it looks like I'll have a critical point of 0. But then again, remember, if this derivative is ever undefined somewhere, that would also lead to a critical point. And sure enough, look at the denominator here. If that denominator was ever equal to 0, so does x squared minus 1 ever equal 0? And yes, it does at both plus or minus 1. So I actually have 3 critical points here. F prime does not exist at plus or minus 1, f prime equals 0 when x equals 0. So 3 critical points to test or to use in my analysis. I'm going to build a sign chart with all of those critical points. So negative 1 comes first, and then 0, and then 1. Label your sign chart with f prime so you know where to plug in test numbers into. So what if I pick a number like, and by the way, there's no closed interval here, so I can go out to infinity. So negative infinity to negative 1. How about I pick a number like negative 2, negative 1 to 0, 0 to 1, and then 1 to infinity. Now I did this ahead of time, but if you plug in test numbers, plug them into the derivative value to see what you end up with. And we should end up with these signs: positive, positive, negative, negative. So to conclude, remember, a sign chart by itself is not considered valid justification. So I would, if I'm looking for extreme values here, it looks like my absolute maximum here is going to have to happen at 0. So I would say there is a local maximum, although looking at this sign chart, there's no other place where it could be higher than, or where the function could grow higher than at x equals 0. So I could say absolute. There is an absolute maximum at x equals 0 because f prime changes from positive to negative. Please do not write any abbreviations. Don't use a plus or a minus in your formal justification. If you want to find what that maximum value is, then simply find plug in 0 and find f of 0 in your problem. So there we go. Those are 3 examples using each one of the 3 methods for finding extrema and how we would justify the extrema in each case. So I hope that's helpful to you, and know that you can use certain tests in certain situations. It's sort of a matter of practicing and getting the feel for which one works best in various situations with certain functions. So as always, thanks for watching, and wish you the best of luck.